Welcome to Tech for Novice channel dedicated to technology-related information for novice in simple language. Thermography Part 1 deals with basic IR theory for thermography. If you wish to watch it, please check the link below. It is the second part in Thermography Series dealing with parameters for measurement and camera. Understanding how these parameters influence in thermography is important if reasonable measurement accuracy is to be maintained. We will explore most important of these parameters in a simple way in this video. Camera parameters are determined by the camera hardware, and most of them are fixed and some are changeable only with extra accessories. However, measurement parameters are constantly changing depending on the target materials, shapes, size, atmospheric condition, environment surrounding the target, angle of view, and distance. We need to understand how these parameters influence the temperature measurement accuracy. If you own or intend to own an IR camera, or you are just curious about thermography or interested in various technology, then you are in the right place. Let us learn thermography with this video designed for novice. Let us start with measurement parameters thermographers need to understand. Thermography cameras requires some parameters of the target and environment for calculation of correct target temperature. They are emissivity, relative humidity, atmospheric temperature, target distance, and reflected temperature. Some of these parameters are easy to determine while some are tricky. Some of them have bigger influence while others have negligible influence, especially for short distance. Emission intensity is proportional to the temperature, and emissivity determines emission intensity in comparison to reference object, blackbody. Therefore, emissivity is the most important parameter for temperature measurement. Unfortunately, it is tricky to determine. Reflected radiation is not distinguishable from emitted radiation, but only emitted radiation is related to temperature. Reflected temperature parameter is used to eliminate effect of reflected radiation. Reflected temperature is neither temperature of the reflecting source nor air temperature. It is apparent temperature of the object reflected from the target into the camera. It is actually reflected radiation measured as temperature. Reflected temperature is called by different names such as reflected apparent temperature, ambient temperature, reflected ambient temperature, and background reflected temperature. Water vapor is one of the main components in the atmosphere responsible for absorbing infrared radiation to reduce its intensity. Relative humidity provides the information on amount of water molecule present in the atmosphere, which can be used to eliminate effect of reduced radiation due to absorption by water vapor. Atmosphere is also a source of infrared radiation which should be eliminated for calculation of true temperature of the target. Higher atmospheric temperature means higher radiation intensity. It also affects the absolute amount of water molecule in the atmosphere, which further affects transmission of radiation. Longer the travel distance, higher the amount of radiation absorbed by the atmosphere. Therefore, it is also included in measurement parameters. Emissivity is the most important object parameter as it determines intensity of radiation emitted by the object in comparison to a blackbody of the same temperature. Actual object temperature can be derived from known emitted radiation and emissivity. Unfortunately, emissivity, though a material surface property, varies easily for the same material. Therefore, thermographers must know factors that change emissivity of an object. Emissivity increases with rough surface and decreases with polished surface. Metals are usually shiny and therefore have lower emissivity, but oxidation increases it. Another important factor is the geometrical shape. Emissivity increases with cavities due to absorption at multiple surfaces. Other factors influencing emissivity are viewing angle, object temperature, and camera wavelength. Emissivity decreases with increasing viewing angle, drastically above 50 degrees. Therefore, viewing angle should be maintained below 50 degrees but not 0 degree, which is perpendicular in our case, to avoid reflection. Influence of object temperature and camera system wavelength on emissivity is insignificant for general-purpose applications. Emissivity is tricky to determine, but we can use rule of thumb if the measurement accuracy is not critical. Non-metals have usually pretty high emissivity and metals have generally low emissivity unless heavily oxidized. Guessing non-metal emissivity is usually safe because small deviation from actual value will not lead to big error in the temperature measured. Small difference in emissivity may lead to big error in the temperature measurement for low emissivity objects such as non-oxidized metals and shiny objects. After converting object signal equivalent to blackbody signal with required correction, object temperature can be determined using known relation between signal level and blackbody temperature. It is the reason for use of blackbodies as reference for calibration of thermography cameras. Next section covers parameters related to infrared cameras and their influence in thermography. Basic concepts of visual digital cameras and infrared thermography cameras are same, both consisting of lens, sensor, processor, and display. Main differences are working wavelengths and extra image processing for temperature measurement. Visual cameras create replica images of objects as we see. Infrared cameras create visible image by mapping invisible infrared radiation intensity emitted by objects. Color images are created by adding different sets of colors to represent different intensity level. Infrared detectors can be divided in two types based on the methods infrared signal is converted to electrical signals for creating images. They are photon detectors and thermal detectors. Photon detectors convert radiation to electrical signal directly. They are more efficient but requires cooling to very low temperature, making the camera bulky and expensive. Thermal detectors create electrical signal using heating effect of radiation which changes resistance of the detector elements proportional to radiation intensity. Thermal detectors are commonly known as microbolometers. They don't require cooling, work in room temperature, and consume very low power. Microbolometer cameras are most common as they are compact and less expensive. IR detectors are focal plane array or FPA consisting of many infrared sensitive cells arranged in rectangular two-dimensional array. FPA detectors are also called staring array as all pixels collect signal at the same time staring at the target. Number of pixels, thermal sensitivity, and detector pitch are important detector parameters. These parameters are not changeable without replacing the detector of different specifications. Low-cost cameras currently available in the market have around 80 x 80 or 6,400 pixels to 320 x 240, which is 76,800 pixels. Camera thermal sensitivity (NETD) or noise equivalent temperature difference is smallest detectable temperature difference. It depends on both detector sensitivity and lens. FOV or field of view is maximum angular view camera can capture. It depends on the size of detector and focal length of the lens. It is usually expressed in angular degree as linear view depends on distance. FOV of a camera can be changed if lens is changeable. Horizontal FOV is denoted by HFOV and vertical FOV is denoted by VFOV. Here is an example of change of FOV with lenses of different focal lengths. Wider the FOV, smaller the image captured by the camera if the distance is unchanged. It reduces the details in comparison to narrower FOV lenses such as telelens. IFOV or instantaneous field of view is maximum angular view each pixel can capture. It depends on size of detector pixel and lens focal length. IFOV is an important parameter in thermography to determine how far an object of certain size can be inspected without compromising measurement accuracy. IFOV is usually expressed in milliradian. IFOV is a constant for a fixed lens camera. Can be changed only if lens focal length can be changed as detector is not changeable. FOV is IFOV multiplied by number of pixels. As number of pixels is fixed, increasing FOV decreases spatial resolution due to wider area each pixel needs to cover. Decreasing FOV will increase spatial resolution due to narrower area each pixel needs to cover. IFOV is an odd term for FOV of 1 pixel. Better term could be PFOV or pixel field of view. Let us review the use of the term IFOV. Detectors used to have only one element during early stage of development, and mechanical scanners were used for creating two-dimensional image. Single-element detectors are still in use as spot meters for single-spot measurement. Some spot meters have additional FPA for two-dimensional IR image without temperature measurement function, which can be used to view temperature distribution. Creating two-dimensional image with single-element detector is a cumbersome process, but no other way if the detectors available have only one element. Here is a concept of creating two-dimensional image using a single element. Detector receives signal from different parts of the object using a mechanical scanner which looks at different part of the object at different time with mechanical movement. Complete FOV is created by combining FOV of single element at different instants. FOV at each instant was called instantaneous field of view, or IFOV, which is still in use for FOV of single pixel of a FPA. Frame rate is the number of image frames captured or displayed within unit time, usually second. It is expressed in frames per second or FPS. It is also called refresh rate and is expressed in hertz. Infrared cameras usually have far lower frame rate than visual cameras. Images could be smeared if the target is moving or camera is shaken during the capture of the image frames due to same frame capturing different positions of the target. Therefore, low frame rate cameras are susceptible to have smeared images. Unfortunately, frame rate of most of the low-cost thermography cameras is around 9 Hz, which is very low. Infrared radiation received by each pixel of the detector is from different section of the object due to scattering nature of the radiation and diffraction from the lens. Therefore, each pixel must adjust signal loss due to spillover to other pixels and gain from other pixels, which requires information from surrounding pixels. It is possible only if object size is several times larger than IFOV or section covered by each pixel. It is the reason spot meter size of thermography cameras usually consists of several pixels, though the value measured and displayed is for a single pixel. Thank you so much for watching. If you like this video, please comment, share, thumbs up, subscribe, and press the bell icon.